Okay. So, that is one of the things. So, even if you get that, even if you from this analysis you get that the smaller the size of the your droplet, the smaller the size of your liquid jet, you will get smaller droplets, but to get smaller droplets you cannot make your orifice size of the injector to be arbitrarily small. You will get clogged orifices and nothing will come out. So, you have to have some ingenious method by which even with finite size orifices you can make good droplets. Okay. The second concern is that you cannot have a liquid jet which just penetrates straight into the combustion chamber, because then it will evaporate, it will break up, atomize at very long distances, and the length of your combustor will become very big. You need to have small compact combustors, because that will cause the weight constraints. The larger the combustor, the bigger the weight it is, because you are housing high pressure gases inside. So, you have to make compact combustors. First of you produce swirlers, which essentially causes the liquid jet to essentially diverge. Sometimes it is a hollow cone jet and diverge. So, you typically use a jet cone angle of about 110 degrees inside a combustor to ensure that the length of the combustor is finite. So, with all these criteria in mind, one has to design this fuel injection, and essentially the whole purpose is that you have to create small droplets so that they evaporate quickly, and then after they evaporate, then this liquid vapor can mix with the air and you can have combustion. So, that is the idea. Okay. So, one as you see that for the liquid injection, the criteria is that the evaporation and mixing should occur with minimum maximum efficiency, and the increase in the liquid droplet size can affect combustion efficiency and pollution level. This is very important, that if you have very large droplets, they will not burn properly, and so it will create local if you have very large droplets, they will take too much amount of time to evaporate, and then you will have regions of large fuel vapor clouds, and there will be not proper mixing. So, essentially we will get fuel rich combustion, and it will cause the production of soot, NOx and what not. Okay. So, and also the injection system should operate at different operating pressures, because sometimes you need more fuel, sometimes you need less fuels. For example, while you are taking off, you need lot of power, you need to produce lot of power, and as a result you burn a lot of fuel and you have to inject lot of fuel, but whereas you are in cruising, you might need lesser fuel. So, that is the thing. Okay. So, typically people do use two kinds of injectors, pressure swirl atomizers and air blast atomizers. So, we will see what they are. We will just give a very brief glance and we will not go into this in details. Okay. So, first is this simplex type of atomizer. So, where you basically use this principle that you create a very small orifice, and a small liquid jet will very narrow liquid jet will come out at very high pressure, and that will quickly break up and atomize. Okay. So, here of course, the amount of fuel injection and the atomization depends on the orifice size, but you see on the other hand you need certain amount of mass flow rate also. So, you cannot have a very small orifice, because then you need immense amount of a pressure drop, immense amount of high upstream pressure to basically push through the small orifice. Okay. So, this design does not work well for a wide range of fuel flow rates, and as such it shows bad performance at higher altitudes. Okay. And this one is a dual orifice atomizer. So, what you have is that this is a cut section. So, it is essentially a circumference like this. Okay. So, this is a circumference like this, and circumferential, and this center, it has basically a orifice for injecting pilot fuel, and it has an orifice for injecting main fuel, and the pilot fuel gives good atomization and low flow rate, and the main fuel starts when the fuel requirement increases. So, this way you can convert a simplex atomizer to basically this dual to operate at for a range of conditions. So, that is the thing, and then you have this air blast atomizers, where you basically use the air, okay, to basically cause a shear on the fuel column itself, so that it can even atomize inside and produce small and small droplets. So, you have basically at this air blast atomizers are widely used in gas turbine engines. So, fuel at low pressure essentially passes over the lip located in high velocity of air, and the minimum droplet size is obtained by the maximum contact area of the fuel and the air. Okay. Because the idea is that if you maximize the contact area, then this the differential velocity between the air and the fuel creates a shear force on the liquid surface, and that basically peels off makes kind of ligaments on the droplet surface, and it peels off the ligaments, and then these ligaments can eventually become droplets. So, for that high velocity air is passed, so high velocity air is passed on both sides of the lip for optimum atomization and prevention of the droplet deposition on the surface. Of course, you cannot allow the liquid droplets to deposit on the surface also, it must be dragged off by the air. And the good thing is that here by controlling the direction of the air, or by controlling the direction of the or the airflow, you can control the fuel distribution. Okay. As a result, it creates less soot, and you can have cooler liner walls, because this fuel is intrinsically comes kind of mixed with air, and the disadvantage is that it has narrow stability limits, and you do not get very good atomization at the startup. Okay. So, this is how a modern atomizer essentially looks like. This is the twin annular premix swirler atomizers which we have looked, which powers this GE-NX engine for the Boeing 787, and you see that here you have this inner, you have essentially the main flame and the pilot flame. So, it is kind of a mix of the different kind of atomizers. So, this side is the main air annulus, which is basically swirled, okay, and this also is the pilot air annulus, and then from here you have the pilot fuel injector. So, essentially, so if you go step by step, so inside you have this pilot fuel injector that goes in, and then these are the swirled where the air comes in, and it's this pilot swirl, this pilot air is essentially swirled, and on the sides here you have the main fuel injector that goes into here, and the main swirl air annulus comes from here. So, this essentially you have twin annular premix swirlers. So, these are this twin annulus that you see here. So, not only once you have one swirler, you have essentially two swirler. For the main air we have for the pilot air, and then we have injection for the main fuel as well as for the pilot fuel. So, this gives you on the sides essentially what we have, because you are allowing in this part, you are allowing the fuel and air to meet before it goes into the combustion chamber. What you get essentially here is essentially a premix flame. Okay. So, that is the good thing about it, and it allows and it allows this flame that you get here is the premix flame, because of the fact that you are allowing the fuel and air to mix before it goes in, and this is seen from here, from this emission images. This blue flame that you get is essentially a premix flame, whereas the central flame you get here, where you do not have the room for this fuel air mixing. You do not want that also, because you want this stable pilot flame inside, which is essentially this orange in color, which is due to the soot, and that is the pilot flame. So, this cuts down the emission to a great level because of the presence of the premix flame, and so even with this liquid fuel injection you can manage to get essentially a premix flame on the main sides, but then that has to be stabilized, and there needs to be a continuous pilot flame for the reasons already discussed, because your power requirement can vary, etc. And this is how the things looks like, the flame surface density, which I have already talked about, and this is how the PIV vector fields inside the combustor looks like. So, you have air coming out from here, you have air coming out from here. So, you have around this region you have a flame essentially shaped like this. Okay. So, these are the main flame regions, these are the main flame regions, this is the pilot flame region. Okay. And you can see this recirculation zone structure that is created due to the presence of the swirlers, and that essentially helps in stabilizing the flame, whereas central you do not have recirculation zone, because from the center you are injecting this straight pilot fuel air mixture, fuel and air separately, and then that creates a pilot flame. Okay. So, this is how a modern what we have discussed essentially. So, that is the idea. You should take it slowly, and you should also consult these books by Lefebvre and Ballal, and also do this analysis. So, once again we have shown you in a very condensed manner that that despite the fact that actual atomization or actual jet breakup process in a combustor is complex, the fundamental mechanism by which a jet breaks up in absence of anything, in absence of air, in absence of gravity, in absence of surrounding airflow or atomization, is this mechanism by which the Rayleigh, we call the Rayleigh plateau instability, which is essentially hydrodynamic instability, where wavelengths which are, or wave numbers or wavelengths which are greater than the circumference of the liquid jets are amplified, and then there is a preferential wavelength of about 9 times the radius, which is the maximum, and typically the jet breaks up into those wavelengths and you get droplets. But of course, in an actual process, this is in an actual engine, this is much more complex, and you need to understand them. One needs to look into the literature and do either numerical simulations or do experiments. Okay, and this is how a practical engine looks like. This is an experimental rig which takes the actual injector from General Electric, and they did this experiments. All right. So, finally, once again you see there is one of the goals, I mean you in an engine is that you have to have a very good temperature distribution at the outlet. Okay. So, all these atomizations, very good atomizations, we can understand intrinsically that that there should be very good atomizations, you need cooling air, etc. But finally, to certify an engine you need to have certain parameters. Okay. As an engineer you need to say that, okay, if my engine satisfies this parameter, I will call it good. If it does not satisfy this parameter, if it comes below the threshold of this parameter, I will call it bad. So, pattern factor is one such very important parameter. Okay. One of the most important and at the same time most difficult designs, as you see here, in the design and development of a gas turbine combustion chamber is that of achieving a satisfactory and consistent distribution of temperature in the efflux gases discharging into the turbine. Okay. And the most important temperature parameters are those that affect the power output of the engine and life and durability of the hot sections downstream of the combustor. The hot sections are the stator blades and then the rotor blades of the turbine. Okay. As far as, and as you see from thermodynamics, for an overall engine performance the most important temperature is the turbine inlet temperature, because you see this engines, gas turbine engines works on the principle of Breton cycle, and to maximize the efficiency the most important parameter that you have at your disposal is this turbine inlet temperature T4. Higher T4, greater is the efficiency, greater is the work done. So, ideally as an engine designer we would like to have maximum as high T4 as possible, which is of course not always possible because T4 immediately goes and hits your turbine blades. So, it is no good if those melts away. Okay. So, this T4 is essentially the mass flow weighted mean of all of the exit temperature recorded from one standard of a liner. Okay. And this is what your pattern factor is defined as. It is essentially a normalized version of your the difference between your maximum temperature and your average temperature at the exit, which is T4. Okay. So, pattern factor is essentially T max minus T4 divided by T4 minus T3. So, T max is a maximum recorded temperature, it can be anywhere, and T3 is the inlet air temperature and T4 is the mean exit temperature. So, this is how you along a turbine blade, this is so from 0 span to 100 span you get, you might desire you might want a design profile like this, but your actual profile might look like this, and then your T max can be something like this. So, the idea is to basically, so and this design profile comes from structural considerations of the turbine blades, materials, stresses, etc. And so, this idea is to minimize this pattern factor as much as possible. Okay. It should be this T max should be as close to T4, because then it means that your entire turbine blade or not only minimum, but you need to have a desired pattern factor, that is your T max should not be too much away from T4 as much as possible, it should be on the lower side. Okay. And your design profile, so that is one number that that is for certifying the combustor. One is pattern factor as a number, that is your T max should be very small, should not have much deviation from T4, but it should not be exactly equal to T4 also, because that is not optimized for if everything is at a constant temperature, then the turbine blades will not like that. Okay. So, there has to be a particular design profile, and your T max minus T4 should conform to that exact design profile, and that is the best thing that can happen. So, this pattern factor, so when you design an engine, when the design consideration for this pattern factor might come from your materials or your turbine considerations. So, as a combustor designer, what you have to ensure is that the output of the combustor conforms to this desired pattern factor, and the output of the combustor temperature profile should conform to the desired temperature profile that comes from your turbine. So, other than that, there can be other things like wall cooling, etc. I will not go into that. So, when you design for wall cooling, you have to consider convection, conduction, radiation, and then a liner can fail if the wall cooling is not proper. Liner can fail due to thermal stress cycles, and to avoid failure, liners are made of high temperature oxidant resistant materials because there is a strong oxidation environment. And as you see that the different times your liner wall temperature can vary differently, so it must be able to take different very high fatigue of it is under very high thermal stress cycles. So that is one very important things, and there are different types of cooling like this kind of wiggle strips, tracked ring, like wall cooling methods, and then you can have transpiration cooling, effusion cooling. You can, if you are interested, you take a look into Lec52's book where these are on detailed, but this is not exactly combustion, but we just show you this for a complete understanding of what are the things required in the combustor. So with that we would end our discussion on the main on the main combustor of a gas turbine engine, and in the next class we will go into essentially the afterburners and how one can understand the stability, how flame is essentially stabilized in an afterburner, and for that we will also look into some of the cutting edge laser based diagnostics that are used to understand flame dynamics in prototypical engines. So till that, goodbye.